All right, dealing with those non-normal variables. Now that we know that they're non-normal, what are we going to do about it? Well, data transformations come in here. Um, some of the basics. There's three common strategies: square root, log base 10, and inverse. If you were not familiar with logarithms, it doesn't matter. It has nothing to do with nothing in this. When data are negatively skewed, these things will make uh, problems worse. So what we're going to have to do is turn it around and make it a positively skewed distribution and then apply one of the transformations above. So it's a two-step process. Some of the code here you can see for performing transformations, pretty straightforward. One thing I want to note is the +1 here. The reason why I'm adding 1 is that some of these transformations, in particular the log and the inverse, do not work if you have variables that have zeros in them. So if you have zeros, you can add 1 so that you have non-zero values. This will another issue. Another issue there is when we have variables that are scaled that have negative numbers, relatively rare. But if it were negative numbers, we'd want to add whatever number would get the smallest number up to 1. And again, if you take a look here, if we square 0, we're fine. But if we log or take the inverse of 0, it throws an error to us because that's not an actual value. R will give you an error when you try to do these transformations. Programs like SPSS will just give you a warning, but will actually give you a new variable that just has the transformation for all the non-zero values. And this has been a point where a lot of people have been tripped up. They get to their data analysis, they're like, wait, what happened to half my data? Well, it's your transformation. So the next step, we do the transformations. Some sources will, excuse me, some sources will provide guides that say, oh, if your data look like this, use a square root. If your data look like this, use a log. I just write the code and then check and see which approaches worked. So we can see this is the mom stuff. The first one is the first 2 is the original one. If we go on down to the one in bold, this is the best transformation. Now, the best transformation, at least for sorry, the best transformation for kurtosis is listed there. It's mom. I'm sorry, I've got the wrong one. I've got the wrong one bolded. It would be wrong. Mom squared rather than mom logged. And then if we look at distance, oops, mom squared rather than mom log, you can see for both the both the skew and the kurtosis, we have that providing the best results. And then for the dad ones, we can see dad logged is providing the best transformation. Now, one thing about this is in looking at these values, we ideally want 0 not to be inside the confidence interval. If we can't get that, we'll just go with whatever gives us the one that gets closest to excluding 0. So it sometimes isn't, okay, well, I fixed it. It's like, okay, well, I made it a lot better. And that's sometimes the best we can do. Taking a look at the shape here, we can see there's a real clear improvement. You can see how much better these look. And if we do a QQ plot, we'll see it's not perfect, but it's certainly a lot better than it was initially. All right, homogeneity of variance. I ran these on the transformed variables, and you can see the new ratios here. The n ratio, well, the n's are basically equivalent, and then the variances are, we didn't get them below 4-1, but we got them a lot better than over 100-1 as we had before. All right, I want to congratulate everybody. Now that you know about transformations, you are officially a transformer. Depending on your age, you will either think this or this. I'm clearly on the Lou Reed side there. And that's a fantastic album if you haven't heard it.